Hi, I'm Brett Handebrink with SciTime Corporation. I'm here today to talk about frequency control basics and why MEMS technology is a great option when considering timing devices in your designs. Let's go ahead and get started. A crystal resonator is a passive device with no power or ground terminals. It is used as the high Q element in an oscillator circuit. A complete timing circuit usually consists of a crystal and inverting amplifier plus two capacitors for the most commonly used Pierce oscillator and parallel resonant crystals. The capacitors and crystal resonator are discrete components placed near the IC containing the inverting amplifier. The crystal is designed to resonate at a specific frequency. If the frequency needs to be changed for some reason, the system designer must use a different crystal resonator. Oscillator circuits using the crystals are designed using crystals calibrated for either parallel or series resonant frequency. Parallel resonant crystals are the most common and require two capacitors to achieve the required 360 degrees of phase shift for oscillation. Series resonant crystals do not require load capacitors. The construction of series and parallel resonant crystals is identical. They only differ in the way the frequency at 25 degrees Celsius is calibrated. While crystals are intrinsically simple circuit elements, their parameters, such as equivalent series, resistance, and maximum drive level, must be closely matched to the particular oscillator circuit in the IC. This is to guarantee startup and proper operation under all conditions. Crystal resonators are usually offered in standard packages by multiple vendors. There are 2 and 4 terminal devices. The package's nomenclature consists of the package dimensions in millimeters with the longest dimension listed first. Each dimension is listed as 2 digits to accommodate decimal values. For example, 3225 means a crystal package which is 3.2 millimeters long by 2.5 millimeters wide. Common crystal resonator footprints are 3225, 2520, 2016, and 1612. This schematic example is from a public Texas Instruments reference design and shows a 12 MHz crystal resonator connected to a dual USB UART IC. The crystal resonator is shown in the blue rectangle, the load capacitors is in the red rectangle, and the integrated amplifier is shown in the green rectangle. It is important to re-emphasize that the crystal resonators are passive devices and require the amplifier and load capacitors to oscillate for a Pierce oscillator using the parallel resonant calibrated crystal. An oscillator is a complete self-contained oscillator circuit containing a resonator, amplifier IC, and any other components which may be required for the particular oscillator architecture. As such, it is an active device which requires power and ground connection. Usually no external components are required, except for the usual power supply filter components and output termination. Oscillators are normally easier to use than crystals because the oscillator manufacturer knows both the oscillator circuit and crystal parameters and ensures they are matched to guarantee startup and proper operation under all conditions. By contrast with crystals, the system designer must consult both crystal's datasheet and the datasheet for the IC containing the oscillator to ensure they will work together under all conditions. Therefore, with the crystal, responsibility for guaranteeing proper startup falls on the system or board designer. With oscillators, responsibility for guaranteeing proper startup and operation rests on the oscillator manufacturer. Oscillators are usually offered in standard packages offered by multiple vendors. The package's nomenclature consists of the package dimensions in millimeters with the longest dimension listed first. Each dimension is listed as 2 digits to accommodate decimal values. For example, 5032 means an oscillator package which is 5 millimeters long by 3.2 millimeters wide. Common oscillator footprints are 7050, 5032, 3225, 2520, and 2016. This schematic example is from a public Texas Instruments reference design and shows a 100 MHz oscillator highlighted with the blue rectangle. It is connected to a TI fractional PLL. The oscillator is an active device and therefore needs power and ground connection. Connected to the VCC supply is an output enable pin and decoupling capacitors. The TI fractional PLL has a single pin reference clock input rather than a 2-pin interface for a 2-terminal crystal. You will also note the absence of load capacitors. The only external passive components needed for the power supply filter and strapping the output enable pin to the desired state, which is always on. As was discussed on previous slides, the clear distinction between crystal resonators and crystal oscillators is passive versus active component. Oscillators are a complete circuit with all oscillator circuit components integrated into the package. Therefore, the oscillator requires a power and ground connection on the printed circuit board. By contrast, a crystal resonator is only one element of the oscillator circuit, namely the high Q reactive element. Therefore, the crystal resonator needs to be driven by an amplifier and may also an additional 2 capacitors in the case of parallel resonant crystals. Normally, the amplifier is integrated into the IC, which is connected to the crystal. Sci-time oscillators replace the crystal oscillators and match the more common oscillator footprints. However, there may be cases in which the customer wants to replace a crystal with a resonator with an oscillator. Some of the reasons have been mentioned before, and the key reason is to simplify the system designer's life and to relieve him from a burden of matching a crystal to the particular amplifier circuit integrated into the adjoining IC, thereby guaranteeing startup and proper operation. While oscillators can definitely make the system designer's life easier, cost considerations may also need to be taken into account. It generally makes more sense economically to replace the crystals with oscillators in frequencies greater than or equal to 50 megahertz. Due to the fact that an oscillator also needs power and ground, the printed circuit board design will need to be modified to accommodate the additional power and ground connections. The first oscillator parameter is clearly frequency. Different applications need different specific frequencies, and these frequencies are sometimes associated with a specific frequency tolerance requirement. In some applications, the frequency tolerance is specified by the governing technology standard. For example, 156.25 MHz is the most often used reference clock frequency for 10 gigabit Ethernet. And the IEEE 800 and 2.3 Ethernet standard specifies a maximum frequency tolerance of plus or minus 100 parts per million for 10 gigabit Ethernet. Fiber channel often uses 106.25 MHz or 212.5 MHz, depending on the serial data rate. There will be more discussion on frequency stability later. The second consideration is output type. The most common output format are LV-CMOS for crystal oscillators and LV-CMOS or clipped sine wave for TCXOs. LV-CMOS outputs drive a single output pin and usually have a voltage swing which is approximately rail to rail. For example, the output clock of a 1.8 volt oscillator with an LV-CMOS output will have an output voltage swing approximately 0 volts to 1.8 volts. Clipped sine wave is often used for TCXOs because they are lower power, therefore reducing the oscillator self-heating and improving frequency stability over temperature. Clipped sine wave outputs usually have a voltage swing of 0.8 volts to 1.2 volts. Higher frequency applications often use differential signaling, which uses 2 signals which are out of phase by 180 degrees. Because the 2 clock signals are shifted in phase by 180 degrees relative to one another and also have lower voltage swing than rail-to-rail, LV-CMOS differential signals reduce the magnitude of electromagnetic emissions and crosstalk. Differential signals are sometimes used at lower frequencies for reduced EMI and better signal integrity. But above 200 megahertz, differential signaling is almost always used. There are several differential signal families. The most common differential signal families are LV, PECL, LVDS, and HCSL. They all have voltage swings in the 7 to 800 millivolt range. And the major difference among them is DC offset. LVDS has a reduced swing at 350 millivolts to 450 millivolts. The power supply voltage, most often denoted as VDD or VCC, is the third most important characteristic. Some oscillators are designed to operate over a wide range of VDD, such as 1.8 volts to 3.3 volts nominal, while others are designed to operate at a specific VDD, such as 3.3 volts. For best performance, filter circuits are often used on the oscillator voltage supply rail and can range in complexity from a single decoupling capacitor for low power oscillators to an RLC network for a high power differential oscillator. Frequency stability is the fourth most important parameter for oscillators, and it specifies the maximum deviation from the nominal frequency in units of parts per million or parts per billion. For many applications, the governing standard specifies the total frequency stability. As was previously mentioned, most forms of Ethernet have a maximum deviation of plus or minus 100 parts per million from the nominal frequency. For example, 25 megahertz is often used with reference frequency for 100, and 1000 megabytes per second. The allowed frequency range would be 25 megahertz plus or minus 100 parts per million. This equals 25 megahertz, or 1 minus 100 divided by 10 to the sixth. Total frequency stability includes several subcomponents, including initial tolerance, frequency stability over temperature, supply voltage sensitivity, output load sensitivity, and aging. Initial tolerance is the frequency stability at 25 degrees Celsius and may also include the frequency shift from soldering the device onto a PCB. Frequency stability over temperature is the maximum frequency change over the specified temperature range supply. Voltage sensitivity is the maximum frequency change over the supply voltage range. This parameter is sometimes broken out separately and other times is included in the initial tolerance specification. Output load sensitivity is the maximum frequency change due to changes in output load. For example, if the load is specified at 15 picofarad plus or minus 10%, this would be the maximum frequency change as the load is varied from 13.5 picofarad to 16.5 picofarad. This parameter is sometimes included in the initial tolerance specification rather than broken out separately. Aging specifies the frequency stability over long time periods, usually years. Because most aging occurs in the first year as package stresses are relaxed, it reduces in subsequent years, and there is usually a first year aging specification, then an aging per year specification after the initial year. An example aging specification is plus or minus 3 parts per million first year, plus or minus 1 part per million per year after the first year. Temperature range is another important oscillator specification. The usual ranges are industrial from 40 to 85 degrees Celsius, extended industrial from negative 40 to 150 degrees Celsius, and this is often required for outdoor telecom equipment which does not have a cooling fan, such as a remote radio head. In discussing package size and type, most oscillators are packaged in industry standard packages in the following footprints: 7050, 5032, 3225, 2520, and 2016 packages. Single-ended oscillators are usually packaged in a 4-pin package, and differential oscillators are usually packaged in 6 pins. Custom programmable oscillators may offer an additional programming pins such as 2 I2C serial programming pins and may come in an 8-pin or 10-pin package. Ovenized crystal oscillators may be offered in significantly larger non-standard packages. In oscillator terminology, X represents crystal and O represents oscillator. Therefore, an XO is a crystal oscillator. This slide explains many subcategories of crystal oscillators. If you look at the SPXO, it is a simple package crystal oscillator, and it is a fixed frequency crystal oscillator in a standard package without any means of frequency control or temperature compensation. Let's have a look at the SPXO categories. SEXO is a simple package oscillator with a single-ended output. These oscillators are normally offered in 4-pin packages. RF SPXOs have low phase noise, including good close to carrier phase noise. Super low power SPXO is used for portable applications with current in the range of 100 microamps to 300 microamps. General purpose SPXOs are used for 10, 100, and 1000 Ethernet with current in the range of 3 to 5 milliamp. DEXO is a simple package oscillator with differential output. These oscillators are normally packaged in 6-pin packages. DEXOs usually have the best jitter performance. SSXO is a simple package oscillator with a spread spectrum clock modulation to reduce EMI emissions. VCXO is a voltage-controlled crystal oscillator. This oscillator has a control voltage input which controls the output frequency and is used as the voltage-controlled oscillator element of a discrete implementation for a phased lock loop. These PLL loops are used for jitter attenuation or clock recovery. TCXO is a temperature-compensated crystal oscillator. TCXO is used in oscillator IC, which has a temperature compensation circuitry to reduce the frequency variation across temperature. TCXOs have improved over the years and have frequency versus temperature stability ranging from plus or minus 5 parts per million to plus or minus 0.05 parts per million. TCXOs used for wireless applications must also have good close-to-carrier phase noise performance. TCXOs used in telecom systems such as IEEE 1588 applications must also have a shallow frequency versus temperature slope, which is consistent over time. VCTCXO voltage-controlled TCXOs have a control voltage input like VCXOs. They're often used for in-system calibration of output frequency. Mobile TCXOs are used in mobile handsets and have a frequency versus temperature performance in the range of plus or minus 2.5 parts per million to plus or minus 0.5 parts per million. The process to create quartz oscillators starting from a quartz bar involves many steps of cutting and grinding. Each of the blue circles represents each one of the 23 steps. Growing the quartz bar itself in an autoclave requires 3 to 4 weeks. Particular importance is set with the stages of the oscillator IC and quartz resonator that are mounted onto the package substrate, and the final frequency adjust is performed. These steps obviously have to be done with the lid open, and there are many opportunities to introduce contamination during the process, especially during the final frequency adjustment, in which an ion beam ablates the metal electrode to the frequency within the required ppm specification. This ablation process is a high energy process which can leave particulate residue inside the package. Any particulate residue left inside the package can contribute to frequency shifts if it makes contact with the quartz resonator. Residue, adhesive outgassing, and stress relief over time also contribute to aging. In contrast to the 23-step process to manufacture a quartz crystal oscillator, the MEMS oscillator fabrication consists of only 13 steps, 7 for the resonator and 6 to package the MEMS resonator with the CMOS IC. Most importantly, the MEMS fabrication process is performed in an ultra-clean semiconductor wafer fab with contamination levels controlled down to part per billion level. The MEMS resonator is encapsulated at the wafer level and vacuum sealed using the SiTime episeal process, which makes the resonator structure impervious to outside contamination. As a result of this ultra-clean process and wafer level episeal, the DPPM is only 1.5 and there have been no field failures attributable to the MEMS resonator. A clock generator generally has multiple clock outputs and uses an external crystal or resonator as a clock source. Most clock generators have one or more phase locked loops which generate multiples of the reference clock frequency. They are often used as the central clock resource for a system and supply most of not all of the clock's needs of the system. In most cases, the pinouts are non-standard, with the exception of the Intel-defined clocks used in servers using Intel chipsets and for some gaming platforms. Using one clock generator for an entire system can present system design challenges. Clock routing is more complicated due to sometimes long traced from clock output to each IC. Long clock traces can result in worse EMI due to longer ground loops. The EMI challenge can be improved by the use of spread spectrum clocking. Clock generators are single or multi-PLL devices which have more than one clock output and which can accept a crystal resonator or oscillator input. Different applications sometimes use different nomenclatures such as frequency synthesizer in wireless applications and frequency timing generators in PCs and servers. Yet, These terms refer to the same thing, a clock generator. Jitter cleaners in normal usage are not really clock generators because they accept a reference clock generated from somewhere else in the system, and their main function, as the name says it, is to clean the input jitter and provide a very low jitter output clock. However, since most jitter cleaners have the capability to be configured as a true clock generator, they are mentioned here. This summary slide presents a simple summary of what we have discussed today. Crystals are passive devices which are used as high Q reactive element in an oscillator circuit. Oscillators are active devices which combine all components needed for the oscillator circuit into one package: crystal resonator, amplifier, and passive components such as capacitors. Clock generators generally have multiple clock outputs generated by one or more PLLs. The oscillator or resonator is usually external. We won't cover this slide since we have already touched on most of the details, but it is a good slide to use as reference for anyone that would like to take a quick screenshot. Similar to the previous slide, this one maps out oscillator types to end application and can be very useful in the future. SPXO has a very broad usage from consumer to industrial and also datacom. VCXO is used in telecom for clock synchronization, clock recovery, and jitter cleaning. Mobile TCXO is used in mobile handsets and also tablets. Stratum 3 VCT CXO and OCXO are used in high-performance synchronization applications such as GPS clock disciplining, synchronous Ethernet, small cells used in wireless infrastructure, and microwave backhaul. Stratum 3E OCXO are used for telecom infrastructure to meet 24-hour holdover requirements. SciTime has every product sector covered with existing devices or devices soon to be sampled except mobile TCXO. Resonators at 2 different frequencies have been sampled to customers, and the super TCXOs, which have also sampled, can compete with a single oven OCXO in some applications. Quartz crystals and quartz resonators only cover certain frequency ranges. Standard frequencies usually cost less because they are higher volume and therefore achieve greater economy of scale. When considering package size, the cost usually increases with smaller package size because smaller packages require smaller crystal blanks, and smaller crystal blanks are more expensive. This is due to extra processing that is required for smaller crystals to reduce the motional impedance. Without this extra processing, which usually involves beveling the edges into more rounded shape to create an energy trap, the motional impedance would be so high that the oscillator circuits would not start up. The extra processing time for smaller quartz blanks costs money and is not totally offset by lower material cost for smaller packages. When you look at stability, the lower stability devices usually cost more because they have additional temperature compensation circuitry, and also because very low stability devices have to be calibrated across more than one temperature. Such testing requires a temperature change and requires time to ramp the temperature to different point. This extra processing time costs money. Ovenized crystal oscillators are the most expensive because they require heating element, temperature sensor, feedback control circuitry, and insulated chamber, which obviously adds extra cost. The other high cost element is the SC cut crystal, which is significantly more expensive than at cut crystals. The highest stability OCXOs are comprised of 2 ovens, one inside the other, adding even greater cost. SciTime has one of the broadest portfolios, second to only Epson due to the absence of mobile TCXOs and OCXOs in the SciTime portfolio. MEMS oscillators have several intrinsic advantages relative to quartz oscillators and SAW oscillators key points, such as shock vibration resistance, resilience to very fast temperature transients, high frequency differential outputs and small package footprints down to 3525, free from activity dips, much better reliability 1.5 dPPM, and any frequency time due to output frequency being generated by a PLL. I have presented a lot of data today. I appreciate you taking the time to watch and learn about the basics of frequency control. Be sure to check back frequently as we are planning to roll out many new products in the upcoming quarters. Thanks for watching.